Hi, everybody. My name is Sasha Berry. I'm with Hype Partners, the marketing and PR agency, and I'm going to be with you for the next couple hours, bringing people on. We're going to keep it lively, going to keep it light. We have the first speaker, Fahim Ahmed, who's going to talk about prop AMMs and why they're so successful on Solana and how they're going to change the world on EVM. Welcome.
Hello, everyone. So today I'm going to be talking about prop AMMs and what has made them work so well on Solana and how they can work even better on EVM. To quickly introduce myself, so I'm currently a fourth-year CA student at the University of Waterloo who previously worked at Base, Axlar, Flashbots, and Amazon. I've also built a lot of Dune dashboards that have hit the front page of Dune. And I've created this write-up on prop AMMs, kind of researching what made them work so well on Solana. And it kind of blew up. And so I've done a lot more research into it and started like reverse engineering some prop AMMs on EVM. And I'm pretty excited to share some of my findings here. So what are some things that you're going to learn from this talk? First off, what are prop AMMs? Why have they taken off on Solana? What are the current challenges that they face on Base, and how are they currently designed on Base? So first off, why should you even care about this? Well, the reason why you should care about prop AMMs is the fact that they've attained a lot of volume in a short amount of time. Like on Solana, they've gotten 73% of volume market share. And just 2 days ago, Will Warren from 0x mentioned on his talk that prop AMMs are now driving 40 to 50% of volume, or 0x's volume on Base, which is honestly incredible. And so here's a quick little graph from sandwich.me from Ghost Labs, where they're showing how tight the spread is on Solana on prop AMMs, like 0.05 bips. Like that is really tight. And to give a quick briefer of what an AMM is before we get into prop AMMs, it's basically just this formula here, x times y equals k, where x is the number of tokens, like token A, y is the number of token B, and k is some constant. And so if you want to swap from token A to token B, you're going to deposit token A, and so that's going to make the value of x go up. And in order for k to be constant, the value y is going to have to go down, and that's the number of tokens you're going to get. And so what actually is a prop AMM? So it's an AMM, except a market maker is actively managing the liquidity on it. And so what that means is that only the market maker is able to provide liquidity. The price curve is what they're going to be updating frequently, and such as like maybe the value k isn't constant. And the price curve formula is actually going to be more complex than just x times y equals k. And so, for example, here on the slide, it can go from like an x times y formula into maybe just some other price curve formula. And so here, like prop AMMs, they work best for short tail, more liquid assets. While AMMs, they serve these like longer tail assets, like meme coins. And so a question that you might ask is, why not like a central limit or a brook? Why not a club? And the reason for that is because like on Solana, if you want to update multiple prices, you're going to have to do multiple update transactions. But on a prop AMM, with just one update transaction, you can update a whole range of prices. And so as a result, it's going to be expensive to update multiple prices on-chain if you're doing a club. Additionally, you can't connect like a club to Jupyter for order flow. But they have a AMM interface. And so when would you use a club over a prop AMM? There's one main scenario, and that's when placing orders is free. So for example, Polymarket, they have an off-chain order matching. And Hypercore for Hyperliquid, they have a free order placement. And so you don't pay any costs. And so why has it taken off on Solana? Well, first off, Jupyter is the main source of order flow on Solana. And so if you want to get that order flow, you got to connect to Jupyter. Second thing is that market makers like Wintermute, they want cheap top-of-the-block updates for market. They want cheap top-of-the-block updates, which Solana excels at because of how cheap writes are. And so, does this sort of environment exist in EVM chains? Well, sort of, but not really. But I'm going to get to that. The first challenge is that there's no main source of order flow. Like, you have multiple aggregators, and you have 0x as one of the top aggregators, but they don't hold all of the order flow. The other challenge is that you're kind of missing, like, updates are expensive on EVM. They're not cheap, and as you can see here, they use a lot of gas units, in the sense where if you want to front run an update, you only need to increment or increase your gas price by 10 times the amount, compared to Solana, where it's 100 to 1,000 times the amount. And so this could be solved by like cheaper SSOR opcodes, or even like a priority lane for updates. But that's like a hypothetical solution. But despite this, you still have prop AMMs starting to launch on Base. And so, like, why is this the case? Before I get into that, the current 2 prop AMMs on Base is from Wintermute and ETHDenver, both of which are accessible through 0x's matcha aggregator. And so, for example, like if you wanted to use their aggregator or use a prop AMM, like here's how it looked like. You just go into their matcha aggregator, place an order, and it'll show you what the route is. And so, how does one of these prop AMMs work on a high level? For example, ETHDenver. I spent some time like trying to reverse engineer their smart contracts, actually, like submitting a lot of transactions through through Matcha in order to land a few transactions in ETHDenver, and also decode a lot of the smart contracts and try to like reverse engineer it. And so this diagram here, it's very simplified, and I'll have like a detailed version in a future write-up. But at a high level, the user, they're gonna submit a swap to ETHDenver. ETHDenver, they're gonna call a pricing contract in order to calculate how much tokens they need to send back to user. If like the quote is stale, such as if a market maker hasn't updated it, then it's gonna fall back to an oracle. And then from there, the user's USDC, like if we're doing from USDC to CBBTC, the user's USDC is gonna go into the vault. And then the amount of tokens that was calculated by the pricing contract is then going to be sent to the user. And so some really interesting insights about this when I was reverse engineering your contracts is that negative spreads cannot be taken advantage of, in the sense where if you have a bid that's actually higher than the ask, an arbitrager can't just buy the bid or buy the ask and sell at the bid. And the spread also appears to increase if like the trader is flagged as risky or toxic. Another thing too is that the spread will also increase if the pool is imbalanced. I'm still trying to reverse engineer the exact number, but it seems to be something along the lines of like 1 basis point per like percentage that the pool is off by. So say for example, if it's like a 60-40 pool, then it'll be a 20 basis points increase. But don't quote me on that. That I'm still reverse engineering. And lastly, there's also like a limit on the number of trades that can occur during a specific block. More details in a future write-up. And so that's just flow for a swap. But what about a flow for actually updating a quote? And so you're going to have a market maker. They're going to interact with the ETHDenver smart contract. They're going to submit an update. And that update is going to store quotes in multiple price contracts. Well, at least some transactions, they do multiple price contracts. And note that this is very simplified. There is some routing that goes on under the hood, but that's going to be in a future update. And this happens every block. So here you can see that you have multiple different addresses calling this update function. And all these addresses are actually funded by the same wallet if you're to look under the hood. And the reason for that, the reason why you have these different addresses calling these update functions is because of the way like Base, they kind of limit you if you are the same address calling like the same function. And so this is just a way to get around the spam limiter. And these update transactions, they consume 54,000 units of gas. And so with that said, how much, like one of the questions you're gonna like ask is like, how much are they spending on these update transactions? Because we've all heard on Solana how they're spending a lot of money, but what about on EVM, where these update transactions are using much more gas units? And so 2 days ago, when I just ran a Dune query, they were using around $30 in total throughout the day, which is much smaller than I would have expected. And the reason for that is because they're only updating like once a block, as opposed to on Solana, where they're having hundreds of updates every second. And a really interesting insight about this is that they don't actually have much of a priority fee. Like, it's basically non-existent. And so with that being said, I kind of want to talk more about like what's next for prop AMMs. And so there's going to be a lot more prop AMMs launching on EVM soon. You kind of heard about that from Will's talk from 0x 2 days ago. And I kind of want to plant the seed about the future of prop AMMs in a sense where you're now having a ton of like tokenized stocks, real world assets, all come on chain. And so how are market makers going to be market making for these real world assets and stocks? Well, they're going to want a way to do so with cheap updates and effective ways of being able to bring those off-chain prices on-chain. And that's where prop AMMs excel at. And so with that being said, that's my talk, and I would love to answer any questions, and also happy to answer questions offline if you want to connect with me on Telegram or Twitter. Yeah.